In this video, we'll use IdaPro and Windbg to do dynamic analysis of an executable. You would use this in malware analysis, crash triaging, or just general reversing. We're going to look at this simple stack and heap.exe program. It's just a demo application for our purposes here. And the very first thing we'll do is use the global flags editor that's included as part of the debugging tools for Windows to enable some additional logging and debugging information in the operating system for that specific executable. So we're going to enable the user mode stack trace and the page heap. In this example, the next thing we'll do is actually run the program and look at what sort of output it gives us. Then we can load it into the disassembler. As far as the disassembler goes, we're going to use IdaPro, which is pretty much the standard. There are a couple of versions. There's a paid-for version. There's IdaPro Free, which is an outdated version, but fully featured. And then there's the demo version, which has some restrictions, like you can't save, things like that. So we'll tell it to go, we'll go work on our own, and then just drag the simple stack and heap.exe into IDA. So we'll take all of the default options, and then IDA is going to ask us for programs that are built with debugging information if it wants to talk out to the Microsoft symbol server. And you always want to do this because this can give us a lot of insight into how the program is written. This specific program isn't something that's owned by Microsoft, so we'll need the actual PDB file associated with the program in order to get anything useful. And that can be really hard to get. So we'll say no to proximity view. And then IDA view A is what we're really going to be doing most of our work in. IDA has tons of functionality that's available in different windows. So here's the IDA function window, and this during the disassembly process, IDA will actually try to determine all of these different function names. And so some of them are obvious, like main, and then for the ones that IDA can't determine the function name, it names it something default, like sub underscore, and then an offset or a memory address that it's located at. If we had symbols, we would get friendly names that the developer used. The imports window gives us a lot of information on what the program is actually doing. So here we see that it's importing a couple of heap functions. It's using memcopy and strlen, so maybe it's doing something like strings. It gives us a little idea what's happening. We can also open the subview, the string subview, and see what all strings are found in the binary. And this can be useful because now we can associate those strings with the output that we saw, and then trace that back in the program to kind of get more information about how the program's running. One thing that we notice here is that there's a test string that's supposed to be put on the heap, and that's not listed here. So just keep that in mind. Sometimes if you go under setup here, you won't see strings because Unicode isn't checked, and Windows applications are often rely on Unicode for a lot of their string stuff. So IDA is pretty smart. It names a lot of things for us. So up here is all of the variables that it's identified. All the variables with positive offsets are all things that are passed as arguments, and everything with negative offsets are things that are local parameters. And so you can see context highlighting here. If we highlight one specific word, it'll show us all the other things that are highlighted, so that's pretty good. Another interesting thing is it tries to do some intelligence with the naming of certain variables. So here it decided to name it DST as destination. And so if we look at memset, just do a quick search for MSDN memset, you'll see that the first parameter that's passed to it is a destination. So IDA knows that because memset is a popular function, a pretty standard function. He knows that it's getting past the destination, so it'll rename things accordingly, which is pretty useful. If you don't really like the graphical view, IDA can also, with the press of the space bar, flip back over to kind of a text-only view. Another really useful feature of IDA is that you can redefine how it interpreted something during its initial analysis. So here we're copying over a couple of D words. If we press the A key, we can convert all of these D words to a string, and that's our test string that we were looking for before. Now, if we press the X key, we can see all of the references to that string, and that's back into our main function where we were initially called from. So that can be really useful functionality if we're trying to find where certain things are happening based on strings in the output. With a line selected, we can also add comments with the semicolons key. So this helps us remember what a certain function is doing or how a certain thing is getting copied. So now we know that the test string is getting printed at the end, and maybe that's something that we want to remember. To scroll, we can use the mouse wheel or just grab and drag the background, and we'll see some of these arrows here. We have a compare and then a jump, and so the green arrows are indicative of a positive branch, and the red arrows are for a negative branch. And if we go to the graph overview and look, we'll see this big blue line, and that's indicative of a loop. We can hit Control and then mouse wheel to zoom out and see what the overall thing looks like. Alright, let's use the debugger now to play around with this loop. So we'll use Windbg, which I think is the best debugger for the Windows platform. To debug a process, we have two options. We can either attach to a process or open the executable. Normally I'd say attach to a process, but since this is such a simple executable, it's fine to just open it with Windbg. So we'll select it, and then we can provide arguments or a start directory if we needed to. We don't need to do that here, so we'll just open. Since it's a console application, Windbg will open up the console window, and then we can see all of the modules and the memory addresses where those modules are loaded at. After the load addresses, it shows that it sent a break instruction, and then we have the values of all of the registers. One thing I want to point out to you guys is notice the module load address for simple stack and heap.exe. It's at 0137. So now if we relaunch Windbg and relaunch simple stack and heap, we'll notice that it loads at a different memory address. This time it's at 002C. This is because of ASLR. We can confirm this with the bang.dh or dump headers extension. Extensions are like plugins, and they're preceded by an exclamation mark in Windbg and provide additional functionality. We'll provide the module load address to bang.dh, and then we'll scroll up. So under the DLL characteristics, you'll see dynamic base, which means that it supports ASLR. And this is pretty much the standard for all of the Windows modules and many of the modules created by software vendors nowadays. Bang.dh will also give you tons of information about the PE headers on the file, so you can see them all there. Another great feature of Windbg is that it has a really extensive help system. You can access it by typing .hh, and this will allow you to search the help system. But probably what's more useful is to use .hh and the command you're going to be executing. So let's do .hh bang.dh. And it'll give us this entire kind of help page about the DH extension and give you all types of information. This can be really helpful, especially when you're starting out. All right. So really the main purpose of a debugger is to be able to inspect a program's memory at any given time in its state. So let's do that. The first little hurdle that we'll run into is there's going to be a different address here in IDA than in Windbg. And so we're going to have to figure out how to match those up. If we look at where the module start address and end address is for Windbg and where the address for a specific call is in IDA, they're much different. So what we'll have to do is rebase the program. We can do this by going to Segments, then Rebase Program, and then simply just pasting in the module load address. So now in IDA, if we select a line and look at the memory address, 2C115F, we know that it at least exists within the memory allocated for the module. So we can use the U or unassemble function with the address in IDA, and what this will do is interpret all of the bytes as assembly at this address. So here we see there's a call, and if we go to IDA, we'll see there's a call, and then there's an add ESP4, and so we see another add ESP4, and then a jump somewhere. So it looks to match up pretty well. So now we'll set a breakpoint on that call to printf. So the module gets loaded at different memory addresses because of ASLR every time the program's run. So we'll use this relative address rather than the hard-coded address to set a breakpoint on, so we can copy and paste it between debugging sessions. So we just set a quick breakpoint, and to show the breakpoints we use BL, and then we can clear the breakpoint with BC star or BC breakpoint number. We'll leave it there and just press go, and now we'll see that our first breakpoint was hit. We did get hit on the call to printf, and so that's exactly what we expected to in IDA. And Windbg outputted all of the values of each of the registers. So you have EBX, CCX, and the rest of them there. Now if we use the unassemble command or the U command on the instruction pointer, we'll see all of the instructions that happen after our breakpoint. And that can be useful for us to figure out, what the program is doing and what it's going to do. And rather than executing the command every time, you can use this disassembly window in Windbg to track that. Another nice feature of Windbg is the call stack view, and so you can constantly watch where you are in the program's flow. And the memory view is pretty nice too. You could watch which values in memory are being changed and display it in different ways too, which may make sense to you or may make it easier for you to understand how the program is functioning. Alright, so now that we have our breakpoint set, let's take a look at the output of the program to see what things look like. So we have a breakpoint set right before the call to printf. So if we press go and tell the program to run, it's going to print inside a loop and then reiterate through the for loop and then hit the breakpoint again. So I'm telling it to go over and over again, and we're hitting that same breakpoint over and over again. Alright, so now if we pop back over to IDA, you can see that whole for loop. But what I'm really interested in is this call to this subroutine. So if I select the line and then look at the memory address that that line is at, I can set a breakpoint with BP and then 2C1171. And that'll set my breakpoint. And I can, if I'm unsure, I can always double check it. I can do unassemble on that address and make sure that they both line up. We got that add ESP4 and the XOR, and that looks good. Now, I don't want to keep hitting the same first breakpoint over and over again, so I'll clear that and then run the program so we hit breakpoint 1 now. And you'll see inside a loop got printed a couple of more times, and now we're stopped right before the call to that subroutine. So right before the call was a push EDX, and so if we look at the stack with DD or display DWORD, we can see the value that's at the top of the stack, and that's this one here. If we look before it, we can see that it's a load effective address. So this is likely a pointer of some sort. And so if we wanted to view what that pointer points to, we can just copy and do DD, and then we'll see the value that's there. To make life a little easier, so we don't have to copy and paste values, we can use this POI function. So DD POI ESP, and it'll treat the value and show the value that ESP is pointing to. So this looks like some data, but we kind of have to look at it different ways to see if it means anything to us. So if we use DB, we can display bytes, and with display bytes, it'll also give us an ASCII representation there to the right. And if we use DW, it'll display it as words, and if we use a capital W, it'll give you an ASCII representation. So here it's clear that this is an ASCII string of test string. And so DA will display an ASCII string and end it at a null terminator. Alright, so now we know what's being passed to the function. Let's follow it in the debugger. So if we use the P command, that would step over the call and just execute it without having us follow it. So we'll use the T command to step into the function, and we can do the equivalent in IDA just by kind of double clicking it to follow the subroutine. And now we see that the source argument is provided. So if we press the N key on the source argument, and then we can name it whatever we'd like to name it. So we can, now that we know it's a pointer to test string, we can name it test string or pointer to test string. And you'll see that IDA updates all the references to it. And if we wanted to be even more thorough, we can use the semicolon key to add another comment there. So we'll just say, hey, this copies a pointer to the test string into EAX. And we can kind of keep that as a note there for us. So you'll see it here written there in the blue. Now if we take a quick skim of the function and all of the calls that it makes, we see one to heap create, to printf, heap alloc, and we keep scrolling down, we see one to memcopy, and then heap free. So what we might want to do is rename this function to something a little bit more useful. So if we press the N key, we can name it to whatever we want to. So here I'll just name it to allocate some heap space and free it, and just press yes to increase the limit, and that will allocate all of the references to this calling function. So if I press escape to go back, I'll see the calling function's reference is properly updated. At this point, I think I want to look at how this program is using the heap. So I'm going to set a breakpoint right before it calls the heap alloc function. So first I'll clear out all the initial breakpoints, and then we'll set a new breakpoint at this 002C1056. And just so I can use those offset addresses, I'll do the unassemble first and then set the breakpoint. And I think I also want to set a breakpoint right before it calls heap free, or before it frees the block. So I'll do that a little differently. Because we're only a couple of instructions away, I can use the previous breakpoint and just adjust the end of the address there to save yourself a little typing. So we'll resume execution with G, and we'll see that we hit our breakpoint right away. And our breakpoint is right before the call to heap alloc. And if we look right after that call, you'll see that something's happening with EAX. And so functions will often store the return value in the EAX register. So if we do a quick MSDN on heap alloc and scroll down to where it details what the return value is, we can see that the return value is a pointer to the allocated memory block. So this is going to be what the program uses to store data, or where the program uses to store data on the heap. And so it'll be kind of useful for us to inspect that value. So we can just use P to step over the call, and then we can look at EAX, which will now contain our heap allocation. So we can do DDEAX or the memory address to see what the heap was initialized with. Another really good extension that's in Windbg is bang heap. So if we use -P-A and the memory address, it'll show us what the user size is and all of the different functions that were involved in allocating it. And that can be really useful to us in things like use after free vulnerabilities when we want to figure out allocation and deallocation points. It's important to note that we wouldn't have all of this information if we didn't enable the page heap and user mode stack tracing. So the next breakpoint that we have set is on this call to heap free here. And what I want to do is we'll resume execution, and then we'll take a look at how that heap block has changed from when we initially called heap alloc to right before we call heap free. So let's take a quick look at the heap block. So you can see that it changed quite a bit. We don't have that initialization C0 stuff. If we do a DB, we can see that actually that string, test string, was copied presumably from the stack onto the heap there. So now we kind of have an idea of how that heap block has changed a little bit. And just for good measure, I'll rerun bang heap P-A in the memory address to see what it looks like before and after. So we'll step over that call to heap free, and then first we'll take a look at our heap allocation. You can see it's all uninitialized now. And if we look at bang heap, we can see a couple of things have changed. So we don't have that user size anymore. So see up on the top there, we still have that user size C when it was in a busy allocation. But now that it's in a freed allocation, that user size isn't there anymore. And also, all of our functions where we allocated the heap block have now turned to all of the functions where we freed the heap block. So if you run bang heap on a freed allocation, you'll get different information than you would on a busy allocation. And then the last thing we'll do is take a look and see how this function exits and returns back to the previous function. So we have our function epilogue here, which essentially redefines ESP to point to the base pointer. And so everything that was on the stack is now uninitialized or not valid because the stack pointer and the base pointer point at the same. So at the base pointer is the saved previous base pointer, and then following that is the return address. So if we do unassemble and the return address, you'll see here that we have an add ESP4 and all that stuff. Before it is what now is going to be the new base pointer, and that will be popped into EBP. So that's what the pop EBP is for. And then the return returns back into this add ESP4. So if we press escape to go back, you can see there's that add ESP4, the XOR, EAX, and then the main function's epilogue. Okay, so we can just type Q to quit, and that will exit out of our debugging session and close down IDA, and we're all done. All right, thanks for watching. Have a good one.